name is Alex Havrilla. I'm one of the co-directors at CarperAI, one of the open source research groups funded by Stability AI. And today I will be presenting trlX, a framework for open source reinforcement learning from human feedback, or RLHF. So what exactly is RLHF? Now, you have probably heard a lot about this recently in the media with the introduction of ChatGPT. But to kind of review it here, RLHF stands for Reinforcement Learning from Human Feedback, and it is a process that roughly consists of 3 steps. So if you're fine-tuning a language model, for example, you first ask your language model to generate a lot of possible responses to a prompt. And then you collect pairwise comparisons for this prompt. So for example, let's say I'm writing a story about like geese, right? So I say, I want to write a story about geese. And then the model generates, okay, one story about a sad goose and then another story about a happy goose. And then I give my preference. And maybe my preference is I prefer stories about happy geese. So this gives me a pairwise preference signal over model generations. And then once I have these like pairwise preferences, I use this to train a reward model, which you can kind of think of as an offline proxy for human preferences. Because what I want to do is I want to optimize the language model that I'm training to be as responsive to human preferences as possible. This is how InstructGPT, for example, was trained. And so this reward model is then trained to kind of assign a scalar value to, model responses which are more preferred is the idea. And so then once you have this reward model, you optimize against it using reinforcement learning. And this is kind of the RL part of the RLHF pipeline. And this is this third part here. And then you can kind of repeat this cycle where once you have this RLHF model, you again deploy it, collect pairwise preferences, update your reward model, and iterate that. And that's the RLHF pipeline. Okay, so what are examples of RLHF models? So these are all examples of closed source RLHF models. So ChatGPT, I'm sure we're all familiar with. Also, Anthropic AI has recently come out with their Claude assistant, which performs similarly to ChatGPT. Also, DeepMind Sparrow is trained with RLHF and does web query type stuff. But these are all examples of closed source models. We don't have access to the data. We don't have access to the training code. And this makes them very hard to replicate and do good science with. And now we ask the question, examples of open source RLHF models. There are none, really. But yes, so actually the flagship product or project of CarperAI is to, create the training frameworks and the data sets necessary to train these large scale RLHF models. Because we believe, kind of fundamentally that the research process and the tools that make this possible should be widely accessible to everyone in the research community. Okay, so why does this matter? Why does open source RLHF in particular matter? So, a couple of reasons. First of all, equal access for all to this kind of technology. I think my general perspective is it is probably unfair in principle to keep this extremely impressive technology locked in the hands of the few. And so I would like to see this democratized. And in general, democratization of AI, I would say, is central to Stability AI's mission. So it's kind of in line with that. But then as a PhD student and a research scientist myself, the third point resonates most with me. And it's that closed source RLHF fundamentally makes good science impossible. And I'm all about good science. So in order to do good science, you need to know all the parameters that went into training these models. So what is the data? What is the training procedure? All these different variables that really have not been studied a lot in the open. And so this is my main motivation, is to open source this entire pipeline. So what are the blockers to open source RLHF? So number one, high quality supervised fine-tuning data. So the first step often when training these models is you need a model which is already pretty good at accomplishing whatever task you want it to accomplish. So you get supervised fine-tuning data, which you can kind of just have the model imitate. And that already gets it pretty good. And it gives it kind of a warm start. And there isn't that much which is available in the open. Number two, high quality diverse preference data. So this is kind of the pairwise comparison data that I talked about at the start. And if you want a high quality reward model, you also really need comparisons which are high quality. So if you're comparing 2 garbage responses, your reward model isn't going to be very good. So you really need to be comparing high quality responses. And this is also kind of highlights the importance of step number 1 as well. And then number 3, we need a scalable training framework for language model fine-tuning via reinforcement learning. And this is a thing which we haven't really seen up until now, since the dominant paradigm for training language models has been via supervised fine-tuning. Okay, so where does trlX, the framework I mentioned at the beginning, come in? So trlX addresses number 3, a scalable RL training framework. And this is a code base that was put out by CarperAI a couple months ago, and it is, as of right now, the most popular choice for open source RLHF. We have over 100 users, have some industry partners that have started using the code base, and in general, it's in a pretty good state. So I guess going into more detail, what is trlX and what kind of capabilities does it support? So our goal in creating the library was to make it accessible to as wide a range of users as possible. And so this means not just users with access to, hundreds of GPUs, multiple nodes, but also users, independent researchers using like a single GPU. We want to make them be able to do some basic RLHF research as well. And so we have different frameworks implemented for different user profiles. The single GPU users can train up to about 1 billion parameter language models, which is decently large. Multiple, users with multiple GPUs can train up to about 20 billion parameter models if you integrate with Hugging Face and use deep speed through their Accelerate framework. And then, if you're a fairly well endowed user with, access to multiple nodes of A100s or whatever, then we've tested even fine-tuning language models up to 70 billion parameters using NVIDIA's NeMo framework. So we try to be quite flexible. Okay, so then in terms of features, what does trlX offer? So there are a couple things I want to highlight here, although this list is far from exhaustive. First of all, we're compatible with most encoder-decoder models, such as T5, and decoder-only models, such as GPT-NeoX, which are supported on Hugging Face, so easy to access these models. We've integrated with some techniques which allow for memory saving and compute efficiency, such as low rank adapters, or LoRa. This saves a lot on your memory while still getting comparable performance when you fine tune. 8-bit Atom, which reduces your optimizer state size. Layer freezing techniques, which reduce the size of the optimizer state and help prevent overfitting. And also this Hydra architecture, which we'll go into in more detail. We've also implemented various reinforcement learning algorithms. So there are a couple paradigms for reinforcement learning that one can explore in this space. One is the online RL, which kind of its flagship algorithm is PPO, or proximal policy optimization. But there are also offline RL alternatives, such as implicit language queue learning. And both of these are implemented and you can run out of the box. Also critical to our RL typically is implementation of some kind of hyperparameter sweep, since RL is famously very sensitive to hyperparameters. And this is built in as well. And then we also have 10 plus examples of varying scope, which you should just be able to get started with, depending on your compute capabilities. Okay, so kind of diving into this a bit more detail, we're going to talk about the anatomy of language model fine-tuning via online RL, at least at scale. And so I think this is important to understand because it gives you a sense of how the library functions and the kinds of engineering challenges that we're facing. So when you're doing language model fine-tuning via reinforcement learning with PPO, there are a bunch of moving parts. So first of all, you have the model that you're training. This is usually the student model, okay? And maybe this is some 6 billion parameter model with a bunch of different layers. So you can think of each of these blocks here as representing a different layer. And typically we freeze the lower trunk of the student model to prevent overfitting and make it easier to fine tune. So that's kind of this gray part here. So this is the student. And then usually on top of the student, there's also this value head, which we stick, which is part of the PPO objective. But then in addition to the student and the value networks, we also have the reference model. And the reference model is kind of a frozen copy of the student model, which is never trained and is used to kind of enforce this KL penalty, which prevents the student model from overfitting to the reward. And this is sometimes useful because the reward models can be overfit too. And then, in addition to supporting inference for both the reference model and the student model, we also need to support inference for these reward models that I talked about, which we trained via pairwise preferences. And suddenly we're talking about, holding in GPU memory at all times, not just the student model, but also the reference model and the reward model. And this can get quite computationally expensive. So one architecture And naively, if you do this naively, these are all three separate models, I just want to say. But one architecture which was introduced in DeepMind's Sparrow paper, which we talked about at the beginning, is this Hydra architecture, where you kind of fuse all of these models via a shared trunk and then split them off at the branches to do, training or inference. And this saves a lot of memory. And it's particularly useful for low resource users who don't have, the ability to even store more space. So we found it's very useful to implement in practice, but this doesn't have to be the case. And in some cases may even impact performance slightly. Okay, so now that we've kind of gone through the setup for, how are these things engineered and what the algorithms are, let's do some examples. So let's say we want to fine tune GPT-J, which is a 6 billion parameter model. And we're going to fine tune it so that it outputs very positive text. So our reward model specifically will be DistillBERT INDB, which is a pretty small model. And its job is just to classify whether a review is positive or negative in sentiment. So our algorithm will be proximal policy optimization, which is an online reinforcement learning algorithm. And the environment we'll be training in is 8 4 gigabyte A100s. And then the trainer we'll be using is DeepSpeed 02 via Hugging Face Accelerator. Okay. And these are the results. So we take 400 steps of PPO fine tuning, and we see that reward goes up very quickly. So the reward is essentially just like a prediction between 0 or 1, which predicts positive or negative. So you can interpret this mean reward as the model outputting very positive text 85% of the time. And then on the right, and it does so in relatively few steps, by the way, right? This is only 400 steps, not that many. So the convergence is pretty quick. And then on the right, we see a couple of statistics here. So there's this X time in the top. What X time represents is the amount of time it takes the model to do rollouts at inference time. So what this is in online reinforcement learning, typically there are two phases. There's a training phase where you train on your accrued experience. And then there's an exploratory phase where you go out and accrue new experiences and store them in some kind of experience buffer. And this second part of generating rollouts and accruing new experience is by far the most computationally expensive part. You can see on average, each time we go to do this generate new rollouts, it takes 3 seconds, which when compared to the amount of time it takes to do a backward pass is like, 600% of the time. So this is really the computational bottleneck, and getting this down is super important. Okay, and so here are some results. Our prompt is, I don't know much about the Hungarian underground. And then the response is culture, but I love this full album. Best tracks are blah, blah, blah. Okay. So, you can see in general, all the responses are rated as very positive by DistillBERT. One thing I kind of want to draw your attention to is in 3 of the 6 examples, you see that the next word is music. Okay. And this suggests that already there's some kind of overfitting of the student model to the reward model. And in general, this happens a lot with reinforcement learning from human feedback, where you observe, your model starts to generate very high rewards, but it overfits and tends to exploit, whatever the reward model thinks is a good reward. So the diversity of generated text tends to collapse as a result. And this is an ongoing problem that we're trying to fix. So some takeaways. The pros of, fine-tuning for sentiment: relatively sample efficient, PPO is relatively sample efficient, and the reward is stable, so the reward goes up consistently. But some cons. So online reinforcement learning with PPO is difficult to scale. Like I said, you need to keep 3 copies of different models in memory each time. And even with Hydra architecture, that's still a lot of memory. And it's relatively compute inefficient. Like I said, to generate rollouts, you got to inference 3 models, and you're not doing this. This induces relatively poor memory utilization when you're doing the rollouts. So it's not very compute efficient. And then it's also prone to reward overfitting. So what's a better alternative? So let's look at a more advanced case study, summarization. So we're going to train a 20 billion parameter model, GPT-NeoX, with a 6 billion parameter reward model, GPT-J, and we're going to train it to generate good summaries, is the idea. So the reward model has been trained on lots of pairwise comparisons so that it has kind of learned what makes a good summary. And now it's going to try to teach the student model what is a good summary. And we're going to do this using offline reinforcement learning instead of online reinforcement learning. And the key difference here is that online reinforcement, we are going to see kind of mitigates a lot of the drawbacks of online reinforcement learning while retaining a pretty competitive performance. So we're going to be doing this on 16 40 gigabyte A100s. And the trainer we're going to be using is GSpeed 03 via Hugging Face Accelerator. And here are the results. So you see that very quickly in the offline case, reward goes up. We reach an average reward of about 2.5, which is decently high. And the metric time, so the amount of time it takes to do, a single, forward backward pass is on average about 3.5 seconds, which when you go back and compare to the amount of time it takes to do, a full training loop for online, the online case is very comparable, right? So this also takes about 3 seconds. But the key difference here is in the online case, we're training a 6 billion parameter model, which is pretty small. And the offline case, we're training a 20 billion parameter model, which is over 3 times as large. And yet the time it takes to train the model is about the same. Which is kind of remarkable. And you're able to get pretty comparable results as well. This is kind of anecdotal, but we have much more. We've ran many more experiments confirming this. And so this kind of suggests to us that you can mitigate many of the problems associated with offline RL, many of the problems associated with online RL while getting most of the benefits. Okay, and so here is an example of fine-tuning for summarization. Here's a story, which I won't read for you, but I suppose you can pause if you want to read it. It's just a story about some, young 19-year-old on Reddit who is struggling for money. And then the summary, which is generated, is I'm 19 with no job. I make around $1,000 a month with car insurance, cell phone, and a RX Jeep. My friend and I are looking at an apartment that costs $450 per month. What should I do? Which I think if you read is a pretty good summary. So some takeaways, like I said, the pros, offline RL is relatively compute efficient. It's easier to scale. And interestingly, we've observed, although it's not demonstrated here, is that it's more robust to reward overfitting. So you will see that kind of the diversity of the text the model generates is much better than the diversity that you get with online training. But the cons is it's a weaker optimization. So, if we really are able to get good enough data and put ourselves in a regime where we want to produce superhuman results, the model does much, much, much better than what experts would do. Probably offline reinforcement learning is going to be more difficult to scale to get to the point where the resulting language model is actually that much more superhuman. So, if we really want maximal performance, we should go with the online RL. But if we're okay compromising and having an easier to scale algorithm and better compute efficiency, then offline is completely fine too. And so I just have this small plot here kind of comparing the two. So easiness to scale, PPO not so good, ILQL pretty good. Compute efficiency, PPO not so good, ILQL pretty good. Robustness to overfitting, PPO not so good, ILQL it's better, but there are still issues. And then high reward. So PPO does do a very good job at maximizing reward. ILQL struggles. Okay. So that concludes my talk. I attached some links here to CarperAI's GitHub and the trlX library in particular, as well as CarperAI's website. So if this interests you, we're always looking for more collaborators. Thank you for your time.